This is going to be the part 5 for the lecture 4. We are going to talk about the redox reactions. Before we actually talk about the redox reactions, I want to actually talk about a little bit of how the battery works, because that's probably the simplest case of the redox reactions. So you have two separate reactions. The zinc with zinc SO4 is in water, and zinc metal here, and then this zinc 2 plus could actually join this this metal piece to become a part of the metal piece. So these things right here could actually go in like this into the part of the metal. But before I actually talk about that one, let's just count the number of charges here. Inside of the water, the zinc is actually having the 2 plus charge, right? But inside of the metal, it's 0 charge, right? Zinc solid, each of the zinc atom having the 0 charges here, right? So how does the zinc 2 plus become zinc 0 charge? That means that the 2 electron has to come from this wire from the top to cancel out this 2 plus charge, right? So I'm gonna have to have 2 electrons coming from the top, right? Those 2 electrons coming in, supplying the 2 negative charge, and then at the same time this zinc 2 plus is going to attach to this metal to become a part of the zinc metal, which is going to be having the total charge of 0, right? On the other direction, the zinc metal could actually dissolve into this water to become another zinc 2 plus. In that case, this electron now has to leave this metal, right? The reason why I'm saying that is because that it used to be at 0 charge here, right? As a part of the metal. But as it dissolves into the water, that also has to carry the 2 plus charge, right? So in order for those to actually have the 2 plus charge, right, the 2 negative charge has to go away as well, right? If you are releasing positive charge, you have to release the negative charge too, right? Because these two things, well, that's exactly the same thing, right? So combining this zinc 2 plus and 2 electrons makes the zinc neutral, right? So the neutral contains 2 electrons and zinc 2 plus, right? But as the zinc 2 plus leaves the rest of the metal piece, that left over 2 electrons has to go out as well, right? So the production of the zinc 2 plus is going to release the 2 electrons. Now let's go to the other side. The copper, this is a copper metal piece right here. All of these things is actually carrying the 0 charge here, right? Now this copper 2 plus in the water could actually become a part of the metal piece, but if that happens, the 2 electron also has to come from the top, right? To make the 2 plus copper 2 plus becoming the copper solid 0 charge, right? I'm pretty much repeating the same explanations for the the zinc portions, but if another piece of copper leaves from the metal, right, to become a copper 2 plus, another copper 2 plus, then the leftover 2 electrons has to move out as well, right? So if the copper 2 plus is produced, then the leftover 2 electron has to go away too. So the 2 electron could actually be produced or eaten by the zinc side, or the eaten by the copper side, or the produced by the copper side, right? So the 2 electron could actually go this way or that way, right? And then 2 electron could go this way or that way, right? But those things doesn't happen until I actually connect these 2 pieces together. If I connect this one right here, what happens actually is that the zinc, let me just try to check the actual case here, because I forget exactly which one is which. I think the zinc, oh yeah, the zinc is going to lose the electrons. So the zinc is going to lose the electrons, and then copper plate is going to absorb the electrons. So the electrons actually flows from those 2 electrons travel this way, like this. Okay, that's what happens. So the copper zinc is going to produce zinc 2 plus, zinc metal is going to release the zinc 2 plus, and then those 2 extra 2 electrons travel all the way down this wire, and then that 2 electrons that's provided to the copper plate will actually be cancelled out by absorption of the copper 2 plus from the solutions. That's pretty much what happens. And all those, if you're wondering what's happening with if the one side is losing the negative charge, then what's going to happen to the whole charge here? It's becoming more negative and negative and negative, right? Less negative and less negative and less negative, right? In that particular case, the Cl minus from this glass tube is going to actually produce the negative charge lost from here is going to be supplemented by the negative charge here. You don't have to actually understand any of these things. I'm just trying to tell you the backside stories of it right now. So, but this is pretty much how the regular battery actually works. The copper zinc batteries, it's very standard one. So this is pretty much how the battery works. We're using the electron that's produced from the one side, and then we actually maybe putting the light bulb or the computer or the cell phones in between, somewhere around here. So we actually have the actual machinery that's actually plugged in, like iPhone here. That's pretty much what's going on here. So that's just the basic stories of how the battery works. I don't think I actually explained very good, but there is so many YouTube videos that you can see, so you can probably take a look at any of those guys if you are interested. For the general chemistry one, It doesn't matter whether you understand this or not. But I hope that you actually get the idea of that this side right here, right? This side, zinc solid, zero charge becoming the 2 plus charge, right? And then the copper 2 plus is becoming copper. So basically that which one is getting positive charge and which one is getting the negative charge. Those are the fundamental interest to many of the reactions, and that's why we are going to run the oxidation reduction reactions. Sorry. So it's not really the battery that we are interested in. Actually, that we are interested in the oxidation reduction reactions, because most of the reaction that's happening in our bodies are actually the oxidation reduction reactions. So it's vitally important for the biological chemistry if you're planning to take one of those classes. Probably like 1/3 of the class is dealing with this oxidation reduction reaction. So someday that those of you who are planning to take the biological chemistry class, you're gonna have to learn this. This is probably the first step. So if the substance is oxidized, then we are actually losing the electrons here. I get confused sometimes, but if the species lose the electrons, so going back to this particular case, zinc was becoming zinc 2 plus, right? If I recall correctly, right? Zinc was becoming zinc 2 plus. So zinc was losing the electrons, right? So zinc was oxidized. It's going from the neutral to the positive charge. So it's becoming more positive. And if the substance gains electrons, we say it is reduced. So for the copper, it was starting out to be the copper 2 plus, becoming copper with a zero charge, right? So it's becoming less positive or more negative, right? So if it's becoming more negative, it's being reduced. It makes sense, right? Because if it's becoming less positive or there's more negative, then it is called reduced. The number of charge actually getting reduced, right? And that's related to the gaining of electrons, because electrons carry the negative charge here. So how do we actually determine this this oxidation reduction reactions? We're gonna define the oxidation numbers. So the oxidation number is just a bookkeeping device. It's not really doesn't have the strict physical meaning to that. I don't think. So but it is super useful. So how do we actually assign the oxidation number to any of those atoms in the reactions? So for example, like what is the oxidation happening for the nitrogen atom in the N2, or what is the oxidation number for the hydrogen atom in H2, or what's the oxidation number of the nitrogen in NH3, or what is the oxidation number of the hydrogen in NH3. Those are the type of stuff that we are going to deal with. The rule that you are going to follow is this whole slide right here. The rule, especially that this one right here, is the strongest rule. Strong. And then as you go down in the table, it's the weakest rule. So you're gonna apply starting from the top and then try to determine the oxidation numbers. And by the time that you're not necessarily going to use all of those guys. You may use just one, or you may use two of these, or you may use three of that, or you may use four of that, right? Or you may use five of those, right? That may be the only stuff that you need. Then you stop right there. So sometimes that you don't use this one, or sometimes you don't use that one, or sometimes you don't use that one, but you are going to use one all the time. So let's just try to figure out exactly what I meant by that. I'm going to go back to this slide so many times from this point on. So nitrogen, right here. Let's just go back to the first one. Oxidation number of any element in its elemental form, the pure element, is 0. So that means that N2 in the pure element, it's 0, right? So the whole thing is 0, whole thing, whole molecule, whole, not molecule, but it's a whole thing. Maybe let's just put the whole thing right here. Is 0, and each one of them has to be 0, right? Because you have two of those things. 0 times 0, 0 plus 0 is going to make 0, right? Now, for we're going to ignore this 3 here because it's not really necessary right now. The H2, both of those are 0, right? Because it's another pure element, right? Carrying the 0 charge here. So the whole thing is 0. Each one of those hydrogen is 0, right? Let's do the NH3 right here. So we're going to ignore that 2 right here. NH3. Oxidation number must sum up to 0 for the molecule, must sum up to the total charge on the ion. So by that statement, this whole thing has to add up to 0, okay? That doesn't solve anything yet, but something that we keep in mind. The next step is a fluorine, but we don't have F here, right? No F in this molecule right here. So the next step is group 1A was group 2A metal. We don't have that one, but we do actually have hydrogen, right? Hydrogen oxidation number is +1. So each one of these hydrogen is having the oxidation number of 1. You have 3 of those, right? So I'm gonna say 3 right here. But remember that second rule right here, the second rule says that total charge, the oxidation number must sum up to the total charge, right? If it's 0, it's 0, right? So this one right here is having the 0 charge right here. That means that if this is 3, then this has to be -3, right? And there is only one nitrogen, so the nitrogen is actually having the oxidation number of -3 right here. Yeah, so you're gonna need lots of these practice things right here. So let's just trying to go back to the what's being oxidized and stuff like those. Okay, so nitrogen atom in N2 was starting out to be 0, it becoming negative 3, right? So nitrogen is reduced here because it's starting out with 0, it became negative 3, that means number got reduced, right? So it's nitrogen is reduced. The hydrogen, on the other hand, started out with 0, it ended up with 1, so it increased, right? So it's being oxidized. So nitrogen is reduced, hydrogen is oxidized. Alright, let's do this one right here. So oxidation numbers. So let's just go MgBr2, okay? So let me just try to write out MgBr2 here, so you don't forget. So ugly here. So what's the important one right here? It's probably number 2. Like we don't have these things applying to this molecule right here. So whole thing has to add up to 0, right? The whole oxidation number for Mg and then 2 of those Br has to add up to 0. That's what it says on the number 2. And then we don't have fluorine, but we do actually have group 1A and group 2A, right? Group 2A, that's Mg. This has to be plus 2. And I have only one of those, right? So 2 Br molecule, 2 Br atoms has to add up to negative 2. Did you get that? The reason why I said that is because MgBr2 is having the charge of exactly 0, right? And if I know that one side is positive 2, the other side has to be negative 2, right? Then each Br has to be negative 1 and negative 1, right? So let's check the answers for that. Good. That's exactly what we have. Let's do this one right here. ClO2 minus. ClO2 minus. So again, that we don't have the pure element, but we do actually have to use number 2, right? That says everything has to add up to negative 1, right? We don't have fluorine, we don't have the 1A or 2A, we don't have hydrogen, but we do actually have oxygen. So each oxygen have negative 2. I have 2 of those. So what this one has to be? Whole thing has to add up to negative 1. Then this has to be positive 3, right? So the chlorine has the oxidation number of 3, each oxygen having the negative 2. Good. So going back to the very first example that I was actually doing, it's this battery things right here, zinc SO4 and copper SO4 stuff. So that's exactly this particular equation right here. And if you recall that this is a molecular equation, we're gonna do the ionic equation, right? So the ionic equation for this one, you're gonna separate this one, right? into the kappa 2 plus SO4 2 minus plus zinc, right? And then that becoming zinc 2 plus SO4 2 minus plus kappa, right? Now, if you actually cancel out the stuff that's happening twice, which is that one and that one, then you're going to produce a net ionic equation which looks like this, right? So let me just try to clean up the things right here. That's the net ionic equations. Then can you identify which one is getting oxidized and which one is getting reduced? Let me just try to give you a little bit of a hint. Zinc solid, 0 charge. Kappa solid, 0 charge. So zinc start out with a 0 charge, end up with a 2 plus. So zinc is oxidized. The kappa, on the other hand, it started out with a 2 plus, it end up with 0, so it's reduced, right? So kappa is reduced. Now, the confusing notations or the definition is that some biologists use this terminologies. If zinc is try to reduce the kappa going from the 2 plus to 0, zinc is a reduced agent, reducing agent. It's the other way around. If the zinc is oxidized, zinc is also reducing agent. I know it's confusing, but it's you just put the agent, then you use a different just side. Like if it's being oxidized, zinc has to be the reducing agent. If the kappa is reduced, right? Kappa is being reduced, then kappa is also an oxidizing agent. It's gonna oxidize the zinc, right? So that's something that you might need to get used to. Then let's do this one right here. So aluminum, for this particular case, aluminum and nickel 2 plus is becoming aluminum 3 plus and nickel, right? We can actually write these things in two separate reactions, just like a previous one. Like this one right here, I can actually make, just focusing on the zinc, zinc is becoming zinc 2 plus and then 2 electrons, right? 0 charge on the left, 0 charge on the right. I just added the required number of electrons to the 2 plus charge, right? And then kappa 2 plus is becoming kappa of solid, which is 0 charge, right? Then I'm gonna have to put the 2 electrons on the left hand side to make it 0. So that 0 electron to start with, 0 electron to end with, right? Whenever you have a 2 positive charge, you're gonna have to add the 2 electrons on that side, right? Those are called half reactions. And if you add these two half reactions, for example, add everything. Zinc plus Cu2 plus 2 electrons is zinc 2 plus Cu plus 2 electrons, but 2 electron is going to cancel out, right? So you get these things like, oops. That's pretty much what you have right here. So I added everything, cancel out the stuff, you get that one. So that's pretty much how the half reaction actually goes. So these particular reactions, you can actually separate this into the two half reactions. Aluminum becoming aluminum 3 plus 3 electrons, nickel 2 plus 2 electrons becoming nickel solid, right? There is a little bit of a problem here. The reason why that I'm saying that is that you have 3 electrons and then 2 electrons here. The number of electrons is not matching it. So that's one issue right here. We're gonna come back to that one. But at this point, what I'm interested is the arrow should pointing this way or arrow should pointing that way? That's the question. So to do that, I'm pretty sure you should. I put the link. I put the link on the video that I want you to see. It's only 15 minutes videos, but that video actually explains like much better than I can explain to you. So that's probably one of the best video that I can find on the YouTube. So please watch that 15 minutes videos, and then that maybe look at this video later. But then you will probably understand a little bit more. The first reactions is actually this reaction, right? And then the second reaction is this reaction right here. So according to what she said is that if your hand moves this way, I guess that I'm not completely understanding how the camera actually works, but if your hand moves this way with the reactant product, then the reaction is spontaneous. That's what it says. So aluminum is reactant, and then aluminum 3 plus is product. Aluminum is reactant, aluminum 3 plus is product. Nickel is a product, nickel 2 plus is reactant. So for this one right here, nickel 2 plus is a reactant, nickel is a product, right? In that case, the reaction actually automatically happens. If your hand is actually not moving in this direction, but let's just say that if it's moving in that directions, so the reactant product in that directions, then the reaction is not spontaneous. The clockwise rotation is the only time that the reaction actually happens spontaneously. So let's just go back to the super beginning of the stuff right here. Zinc with zinc reactions. So zinc is becoming zinc 2 plus, and then copper is becoming copper 2 plus, copper, right? That's pretty much what was happening, right? I guess that I should probably write these things this way, 2 of those, and then maybe plus. I'm running out of the space. I'm gonna write it right here. I was actually talking about this particular reaction here, which was that one, right? Zinc is becoming zinc 2 plus, and then copper 2 plus is becoming copper, right? So copper 2 plus is becoming copper, zinc is becoming zinc 2 plus, right? So zinc right here, I start out with a zinc reactant. This is reactant. Zinc 2 plus is a product, right? And then copper, where is copper? Copper 2 plus is a reactant. That's reactant. And then copper is a product. You see that? It's going this direction, right? Reactant, product, reactant, product. It's a clockwise rotation. So that means that this reaction automatically happens, which means that that arrow is pointing this way. That's what's going on. Now let's go back to this particular reactions. So I said something wrong, right? Because the charge is not balanced, right? Because if I add the whole thing, I have 2 plus on this side. If I add the whole thing, I have a 3 plus. Charge is not balanced. There is a problem here. So how do I actually fix that one? What if I actually multiply these things by factor of 2 and then multiply this one by the factor of 3? Then what happens is that I have 2 aluminum solid becoming 2 aluminum 3 plus and then 6 electrons, right? And then I multiply the nickel side of it, multiply by 3. Now 6 electrons to cancel the charge is becoming the nickel, 3 nickel solid, right? And that 6 electron cancel, you get this things right here, which the 0 charge, the 0 charge here. So that is perfectly fine. So I guess that you can probably do this reaction by yourself. I think after you watch the video, it's even easier for you to figure it out. So I'm gonna stop right here, and then yeah, just please watch the videos on that one. That she's really good. So I guess that probably the only place that I should probably mention to you again is that this particular table right here. I think she probably uses a different method here, but for this particular class, you're gonna have to stick with these things, okay? So use this table and then know how to use this table. I think that's pretty much the whole point of this lengthy videos. Thanks.